So I think the code is from Tuesday, I believe. And this is how we formalized Schroeder-Bernstein. We said Schroeder-Bernstein theorem as its input takes two functions, f and g, let's say. And then it says if f is injective and if g is injective, we really don't need brackets here. I mean, no harm, but we don't need it necessarily. Right, so if f is injective and if g is injective, then there exists a function from a to b which is bijective, right? And let's recall that bijective means being injective and surjective. So to prove this, we said, okay, because we are proving an implication, we have to say, okay, let this be true. So this means let f be an injective function. And this says let g be an injective function. And therefore, we have to provide, after this, the goal is to provide a function h, which is bijective. And to fill this existential quantifier, we are going to provide a function here. So this is the place we are naming the function. And once the function is named, we have to prove the property that it is bijective. So there are two pieces of data that we have to provide, right? So here we actually provide a function. And here we show is actually bijective. Okay. So far, so good, I hope. But we sort of thought, okay, maybe this is a bit difficult to prove for any types A and B. And this is what we did in informal treatment of this theorem as well, right? So we said maybe we can prove a more simple case where the type A, it's going to be the left closed, right closed interval 0 and 1. And in Lean, we actually express it as ICC01. So I stands for interval, C for left closed, and this C for right closed. So this is going to be our type A. And this is going to be our type B. And we had a function from the closed interval 0 and 1 to the half closed one, right? Does anybody remember what that function was? No? So it takes some number between 0 and 1, which can potentially be 0 or 1, and it has to produce something between 0 and 1, but not 1. So what can that be?
You can just take each thing in the domain and like divide it by 2, for example.
Right. Divided by 2 or 3 or 4 or whatever, right? Because in that case, 1 gets a strictly less than 1, like it gets either half or third or whatever. So definitely when we apply that function to 1, it's going to land in here. And anything else as well gets smaller than what it was before. So, and because it was already between 0 and 1, it's going to be still between 0 and 1. So that's one function. And in fact, this is how we implement it, right? Now, I want you to look at this and see if you can make sense of it, like what's going on here. Why do we have a bracket that has two things in it? So I'm defining a function from this type to this type, right? And I'm saying, okay, I take the input x that comes from here. So x is going to be a number between 0 and 1. And I'm returning something like this. And why is this a pair? Shouldn't be just a number between 0 and 1? You can just guess. I mean, it doesn't have to be correct. So if there is no suggestion, I'm going to ask it, maybe Copilot, to tell me why function f has two parts. So let's see. The function f has two parts because, and let's see what it says. Okay, almost got it right, but not completely. It says we need to provide a proof that x half. So x dot val is essentially x, because we need to provide an output in this case, namely x over 2, and a proof that x over 2 is in 0 and 1. Does this make sense?
Wait, sorry. So there's like multiple layers of square brackets going on. There's the yellow ones,
Right.
which is the yellow ones that we're talking about. The first part is the value, and the second part is the proof.
Right.
But then inside the second part, there's another like pointy brackets, which what I'm confused about with the two parts.
Right. So I mean, you're correct. You have every right to be confused because we actually haven't talked about what sort of object this is. It is a type, but it's a type in a weird way. So we are going to talk about it today a little bit more. But maybe just to answer your question, so the yellow bracket is what we are talking about, right? It's a value plus the fact that the value has the property of being between 0 and 1. So that property is proved in here, right? The second pair of brackets, which are these purple kind of brackets, is that what your question was about? So that's like, so if I start this proof, right, my goal is to prove that, first of all, we don't understand what this up arrow is. So we are going to learn about this today, but for a moment, let's just ignore this up arrow. Let's just read that as x. So our goal is to prove that x divided by 2, it's in the half closed interval 0 and 1. Half closed, half open, essentially. So that means x divided by 2 is at least 0, but is strictly less than 1. How do we prove this? Well, we have this hypothesis which says x belongs to this closed interval 0 and 1, right? So what does that mean? That means x is a number which has this extra property that is between 0 and 1, right? So x itself has two pieces of data, a number and a property. And whenever we have such a thing, we can use this tactic obtain to break it into two parts, right? So if I do that, what do you expect to get after obtain? So if I put my cursor here, what do you expect to get? So I can also like break down x into two other names. Like if you like, you can call it like val and prop, which we did before. And now when I put my cursor here, I get a value, which is essentially x, and a property which says x, or the value of x, is between 0 and 1. Right? So that's what obtain does. Usually when you have a thing that has a property, you can break it down into parts. And now I'm going to simplify this property. So because to belong to this interval essentially means being between 0 and 1, right? So if I do that, and maybe actually I want to simplify it everywhere. So simplify at ternusol, it means simplify at the goal, right? So if I just write sim, it does the same thing, right? The goal got simplified because before it, the goal is something complicated now. So it simplifies the goal and saying that half of x is bigger than 0 or equal to 0, and also is less than 1. What if I also wanted to simplify here, like simplify this expression? Well, I would simplify it everywhere. Well, that didn't do much, actually. That didn't help. And now my proof doesn't work. So let me go back to see what we've, so before this, I see. Okay. So anyway, before this, I have this complicated expression, and I want to simplify it essentially. So we can't understand yet what this complicated expression is because it depends on this up arrow that I haven't explained yet, but we'll get there. So right. So after this, my goal is a conjunction, right? And I can prove a conjunction by proving each part separately. So that's what the constructor does. Okay. So the question is like, why is this val over 2 is bigger than 0, and why is it less than 1? Well, we have to use this prop at some point. So maybe instead here, I want to simplify it at prop, right? So that, because you see, prop is quite complicated. Well, it says the value is between 0 and 1, and I want to simplify that to an inequality. And that's what it does, right? And I'm using now this inequality to prove this one. And that follows from this linear arithmetic, essentially. So this was like a high level view of this, but we are going to get more into the details of what's going on here. But maybe a high level view is like, we needed to provide two things because we needed to provide a value and prove that value actually belongs to interval 0 and 1. Any questions about this? So, but before going further, because things are going to be a little bit more complicated, I want to focus on this first, and let's try to understand how this is constructed. So what is this ICC? Or maybe what is ICC of 0 and 1? So
the closed interval. Oh, sorry, go ahead.
No, go ahead.
I was gonna say the closed interval that includes 0 and includes 1. Exactly.
By the way, you can interrupt me anytime, so you should speak and just like cut me off anytime. That's completely okay. So you should not apologize for this. But you're right. I mean, so that's our idea that this is interval 0 and 1. But actually, Lean curiously says this is set n. What is set n? So let me copy. I think if I click on this, it copies. Yeah, okay. So when you click on this, actually it copies whatever the result of check is back to your file. Okay, so what is set n? Did we ever discuss this actually? By the way, I can sort of coerce this to be set of R as well if I wanted to. So that also works, but it seems like the default value is set n, and if you wanted to force it, then it can be set R. But the question is like, what are these things, set R and set n? So I don't know if you remember, but very briefly, we talked about this in the very first lecture when we introduced types and type constructors. But other than that, we actually haven't had time to talk about these things. So maybe I start a new file, which I have already. It's called, I put it here, basic.lean under the folder set, in which we are going to understand what this set business means. So if you look at the folder source, there's a subfolder called set, and set basic has all what you need to know about sets essentially. So I suspect you will need this file for the next homework questions. So you have to go through this and understand what all this code is and dilemmas and theorems in here. But essentially today I want to like start a new file, going through some of this stuff, like as a sort of demo. So here's the file. This is in the demo essentially, demo sets basic. Right. So we are wondering what this business set X is. So here, X is a type, and set X as a new type is defined as the type of functions from X to prop. Does anybody remember what is a name of a function from X to prop? Like if I have a function, let's say I name it F. So if I have a function like this, what did we call such functions? We had a special name for them. Nobody remembers this? So we actually called a function like this a predicate. That means it's sort of like it's a bunch of like family of propositions depending on the input X. Okay. So for example, even was a predicate on natural numbers, right? But now I'm defining this type set X exactly to be the type of predicates on X, right? The reason for that is because if I have a predicate even, which says if a natural number is even or not, I want to form the set of all even numbers, right? This, let's say, so I want to form here, this would be the subset of even natural numbers. So this means I want to look at all natural numbers and select only those ones which are even and put them somewhere in some type. And this is how I do that, right? So set n essentially means a subset of natural number. The type even is one such subset. So maybe more, I mean, if you want to see exactly the long description of these things, this is what I wrote in the source file. So that a set S in U is just a predicate S from U to prop, and we should think of S as a collection of all elements U in U. So we change all U to XS. So let me change it here as well. So a subset S of X would be just collection of all elements in X that satisfies the property S. So that is all those X for which S of X is true. And sometimes, like in traditional mathematics, you see notations like this. So this is the so-called set builder notation. So we collect all X, little x from the type X, which have the additional property that S of X is true for them. Any questions so far? Okay, so what I did here, essentially I picked all the even natural numbers. So since subsets or sets are defined as predicates, everything, so basically to prove things about sets is exactly the same or very close about predicates. Okay, so what do I mean by this? So for example, so yeah, so this is essentially today's lecture, like that we are going to explore like the logic of sets. So let's introduce maybe a section in which I introduce some variables. And let's say that I have variable A, B, and these are subsets of natural number. And I write such a thing as A sub B. So how are we supposed to interpret this? Maybe Langi, you want to say something about this?
It's a little bit confusing. I'm still processing.
Mm-hmm. But have you heard of this notion of subsets before this?
Yes, of course.
So in and there, what do you think? Like, what does it mean to you when we say a subset of B?
It's like every element in A is in B.
Exactly.
Yeah.
So this means for every X, for every natural number N, let's say, if N is in A, then N is in B. Okay. But because we understand sets or subsets as predicates, to say that N is in A, it's the same thing as saying, so let's translate this, right? To say N is in A is the same thing as A of N is true, right? So for example, when I say here that, for example, if n is in the subset even, so this is the subset of all even natural numbers, then even n is true as the predicate. Okay, so this might be the most delicate part, to identify subsets and predicates, right? And the translation essentially goes like this. If I have a predicate S, then I can understand it as this set, the set of all x for which S of x is true. And we are essentially identifying even with the set of all natural numbers for which n is even. And now with this kind of interpretation, let's translate what Langi said, which is for every natural number n, if n is in A, then it's in B. So therefore, the statement that every n is translates into so it says for all n, if A of n is true, then B of n is true. So that's the meaning of A being subset of B, right? So let's create an example for this. So let's define, so for example, we can define all the natural numbers which are divisible by 4, right? So we need a predicate to do that. So numbers which are divisible 4. Okay. So first we define the predicate. Or first we define it as a predicate. Okay, so maybe I write it like div by 4 for the lack of a better name. So how do I define it? Well, I take a natural number and I have to return a proposition. So what should this be? Well, it should be that n is divisible by 4. So to write this, I can use this notation. 4 divides n. I think I need some, yep. Okay, so maybe I write this. So now I can immediately turn this into a set, or rather a subset of natural numbers, right? I can consider it as a set of natural numbers. Simply because set n is exactly defined as n2 prop. And because this is a function from n2 prop, it's also going to be a subset of natural numbers, right? This works because set n is defined as n2 prop. And because this term and div by 4 is a term of nat2 prop, so it's a term of the right-hand side. And therefore, because these two things are equal, it's going to transfer and become a term of the left-hand side. And now we can actually prove, or at least we believe that if I look at the set or of all numbers divisible by 4, that should be a subset of even numbers. So let's try to prove this. Anyone, maybe, does anybody want to say something? How do we prove this? So what am I proving here? What sort of statement is this?
You're proving that for any number that is in the set divisible by 4, it's also contained in the set even. So they'll all be even if it's divisible by 4.
Absolutely. And because, as you said, we are trying to say for all, right? For all natural numbers, which is in the first set, like div by 4 holds for that, then it's even. The first thing we do is to introduce this n, right? So we say, let n be an arbitrary natural number, essentially. Okay, I'm getting an error here. If I finish, sorry, would that not work? Okay, this is a serious error. What are the messages? As subset n to prop. What if I force this to be considered as a set of natural number? Maybe this as well. Okay, still doesn't work. And to prop. Okay, we can do one trick to make this fork, I guess. So let's define a sort of like, just some arbitrary notation. Something like set of. Oh, set of has already been declared. Maybe in mathlib somewhere. Okay, what set of says is if I have a predicate on a type alpha, right? So far we have worked with x, so let's call it x. If I have a predicate on x, then I can make a subset out of it by essentially copying it, because these two types were defined the same. So hopefully now I can just write, instead of coercing like this, I can just write set of all natural numbers which are divisible by, or it's going to be subset of set of all natural numbers which are even. So let's see if this works now. Okay, now Lean is happy. Great. So let me close all these messages. I hope this didn't confuse many of you. Essentially what I had was like a predicate here, and I wanted to turn this into a set of all numbers that satisfy that. And this function set of does that for me. Right. So set of changes this function. Maybe I should write. Turns any predicate P with a set of elements that satisfy that predicate. There's any predicate P on X. Great. So because this is a predicate, we want to consider the set of elements divisible by 4. And then here I want to consider the set of even numbers. Okay, so maybe I want to simplify this, right? What does it mean that n belongs to that? So if I write dsimp in the goal, that simplifies the meaning of n belonging to a subset to basically saying that n is divisible by 4. Right? So let's look at this again. This says if n belongs to the set of divisible numbers by 4, then n belongs to a set of even numbers. But remember, how was this set defined, set of? Well, it was just all natural numbers which are divisible by 4. So in other words, this premise here says n is divisible by 4. And the conclusion says n is even. And dsimp exactly does that. It simplifies. Okay, now how do I prove this? Well, this is an implication. And to prove an implication, we have to say, let the hypothesis be true, right? So we say intro H, which is suppose that n is divisible by 4. And now my final goal is to prove that n is even. How do I prove this, knowing H?
Can we do the thing where we rewrite n as like 4 times k and then turn that into like a 2 times k and then say that that is
Right.
even, or if that's
Right.
divided by 2?
So we have to understand, so H proves that 4 divides n, right? But really, what does 4 divides n means? Means that exists some k such that n is 4 times k. Do you agree with this? So H is a proof of this statement. And now, because we can break it down into 2 parts, right? We can break it down into a k and a proof of this identity. And how do we do that? What was the tactic to do this? So break down H into 2 parts. A number k and a proof that n is 4 times k. Well, if you remember, this was obtained, right? We have done this now a few times. So I can say obtain a pair k and hk just from H. Great. So we got a number k and a proof that 4k is n. And how can I use this to prove n is even?
Take out a factor of 2 from hk, like like rewrite it, I guess.
Okay, yeah, that sounds a good idea to me. Yeah, maybe usually have is good friend here, right? So maybe we write have n, and this is our goal. 2 times k. Somehow from hk we have to prove this, right? So right, by what? Rewrite h, does it? hk. Oh, apparently it doesn't. Yeah, because if you rewrite hk, that means I'm going to substitute. So I want to prove this, right? That n is 2 times k. Well, if I do rewrite hk, that's going to replace n in here by 4k. So you get such a goal that 4k is equal to that, right? So therefore you need to do more a little bit.
Did you say like by ring?
And now we can do, exactly, we can do by ring. Right? Or that is maybe quite a big sledgehammer, you know. Maybe we can do by maybe associativity of multiplication, right? Because we want to first rebracket this to write 2 times k, and then 2 times 2 is 4 by reflexivity. So maybe we can write mol assoc. But backward. And now there's nothing to prove. But ring as well does that. So, but ring is a really powerful tactic. Okay, how do I prove now n is even? There's still a goal left.
I don't know if we have to like, maybe we don't have to group the 2 times k. Can you just like use this?
You mean exact this?
Maybe.
No. Well, what is the error message? It says this has type n 2 times k, but is expected to have type. I cannot read the rest of it because I have this zoom window. But what does it say? But it's expected to have type.
Oh, even n prop. Maybe we could do obtain again, but like the other way. I don't know.
What if we unfold even in the goal, right? Okay, so that shows exactly what we need to prove.
Oh, we want it to be something plus something. So maybe we can change
How do we
this
prove
to be
existentials?
k plus 2k.
So this starts with an existential quantifier. How do we prove usually an existential quantifier?
We use use.
Exactly. So we prove the existentially quantified goal by providing a number R which has the property that n is equal to. So what is, use what? What is your candidate for R? So for which number R, it's true that my n is R plus R.
2 times k.
Yeah, so all we need to do is to look at this, right? So let's use 2 times k. Great. Now, maybe exact this would work. What do you think? Would it work if I write exact this?
Wait, but this is still the same statement. Do we have to rewrite this? such
I'm
that
afraid
it like
yeah. So it's not exactly right because one has like addition, the other has, and Lean here is being like pedantic, really super pedantic, because it wants us to prove that 2 times 2 times k is 2k plus 2k.
yeah.
So maybe what we need to do is actually to tell Lean that fact. Like that rewrite, there is a lemma called 2mul, which does that. Like 2mul says, 2 times n is n plus n. And that's what we want to do, right? So maybe if we do that, but rather backward in the goal, then our goal changes to exactly what this proves. Did I go over this step fast? So you see 2mul proves that 2 times n for any number n is equal to n plus n. Now, if you look at our goal also has n plus n for n being 2k, right? So it has the form 2k plus 2k. I want to replace 2k plus 2k by 2 times 2k. And if I write backward along this substitution, it's exactly that. Right? It replaces something plus something by 2 times something, but from right to left. So this rewrites 2 times k plus 2 times k in the right-hand side of the goal by 2 times 2 times k. Great. Now our goal doesn't have any addition. It has only multiplication. And the goal is exactly what is in the assumption, right? This proves that. So I can write exact this, and then we are done. I could as well here rewrite and use assumption at the same time, right? So instead of rewrite, I would write RWA. So if you write, you can combine this exact and rewrite in one step, and that is RWA. So then you don't need this. Okay, so so it rewrites and then uses one of your assumptions to close the goal. Okay, great. We proved a very basic fact. I wonder if I had this and I use this first intro n and then symph. Okay, it brings us there. So it's a little bit faster maybe. Not much. I mean, it's going to be the same. And then after that, maybe we do, does linearity prove such a thing? No. Tauto, no. Okay, so I don't think I can necessarily give a much shorter proof than this. Okay, so there are operations on sets. So what are the operations on sets? So if I have two subsets of natural numbers, let's say evens and odds, I can take their intersection, which would be empty because there is no number which is at the same time even and odd. I can take their union, which is like putting all elements of each of the subsets into one big set. And the union of evens and odds would be all of natural numbers, right? I can take the difference between two subsets, meaning that elements in one which are not in the other. So there are a bunch of cool things that one can do with sets. And I want to, for example, let's try to define unions of two sets, right? So if I have like A and B, I want to define union of A and B. And I hope that you have seen this notion before. So let's say if I want to define, let's say, union, right, of two sets. So I take A and B as subsets of natural number, or subsets of any other set X. That's also fine, more general, And I want to return their union. So the type of this has to be set X as well. Okay, but how do I define it?
So for element in set X, it is either in set A or in set B.
That's right. So I have to say, take all x's, right, such that either A of X is true, or maybe we should write it. We can also write X is in A or X is in B, right? So that's one way to define it. And if I wanted to define this in terms of like predicates, right, because we can understand A and B as predicates as well. How do I write this as a predicate? So now it should be a function from X to prop, right? Because it's a function from X to prop, I write 1x, but what is after that? I guess like, how do we translate this part into a proposition? So think of A to be subset of even numbers, right? To say that X belongs to even is the same thing as writing even of X, right? So this is the same thing as writing A of X. And similarly for B, so that's another way to define union, maybe alternative. And actually, this notion is already defined in MATLib. And so if we check big union, you can already see that it's defined in MATLib. But I think this is, this is the wrong union. This is a union of some for types. What we want is for sets, essentially. So therefore, we need to say maybe set union. Yep. So either we have to write set union, or we can open sets, and therefore we don't need to write union. Sorry, we don't need to write sets, I assume. Sorry, this should be namespace. So in the namespace set, we don't need to write sets, but it seems to not work. Okay. I was hoping that when I'm in the namespace, I don't need to provide set dot. Usually that's the case, but I don't know why it's not working in this case. At any rate, there is this notion of set union, and then there's this notion of set intersection. Is it like this? Apparently not. I think it's just inter. So this takes intersection of two sets. And actually, we can inspect how it's defined, right? We control click here. And so if S1 and S2 are two subsets of type alpha, we can produce a new subset of alpha, which is their intersection. And it's defined as collection of all those elements A, which belong to the first subset and belongs to the second subset. Similarly, you can see that in MATLib, there is a notion of diff. So when I say MATLib, look at the path here, right? So we are in the mathlib. There is a folder called init for initials. And then there is set.lean. There is a notion of symmetric difference. There's a notion of power set, and so on and so forth. But let's start like maybe experimenting with a few of them, like prove some stuff about them. For example, we might be interested to prove that if we know that we have a subset of B, and we want to take intersection of this two subsets with another subset, let's call C. So I take intersection of C and A, and I want to prove this is still subset of intersection of C and B. So if I wanted to prove such a thing, how do I start? Actually, maybe I want to say for all C subsets of natural numbers. Okay, if I do this, what happens? Nothing. Yeah, because A and B were already declared at the beginning of the phi, I think somewhere here to be subsets of natural number. And I'm saying if I have another subset of natural number, and if I take the intersection with the first set A, that's going to be subset of C intersection B. So where do I start proving this goal? So because I'm starting with a universal quantifier, I'm going to say, let's see, be an arbitrary subset of natural number. So that's going to give me C in the context. So C now is a subset of N. Set of natural number is a set. So it's not the set of natural number, but a set of natural numbers, which means like some of them, maybe, not all. And now my goal is to prove this first intersection is subset of the second intersection. How do I do that?
Also intro like CA, which is something in C and A.
So I can definitely intro some elements in C intersection A. So that's going to be, let's say, intro X. So when I did this, I immediately get a natural number X, arbitrary, right? And now my goal changes. If X is in the first set, then X is in the second set. So if you're interested, you can, for example, unfold definition of intersection. And this you can do with unfold or rewrite. So what I can do is mem inter if. Oh, that doesn't do anything. Okay. I guess I could have opened sets and then I didn't need to write this. Yep. So this lemma says essentially it's an if and only if statement, which says an element is an intersection if it's in both of them, right? And because if and only if are like equality, like between propositions, you can rewrite along them. So you see, before this, your goal is X belongs to this, then X belongs to that. And now I'm just simplifying what's the meaning of intersection, right? So after this, my goal is if X is in the C and A, then X is in C and B. And now I want to also simplify the meaning of intersection in the second, in the goal So maybe I want to, do it twice. Okay, we just simplified the goal by simplifying what intersection means. Right? Great. And now we are proving an implication. Therefore, I have to say, okay, let the hypothesis be true, right? So you can do intro H. So that adds an H, which is an assumption saying that X is in C and X is in A. And now I have to prove a conjunction. How do I do a conjunction?
Use constructor.
Exactly. Okay. How do I prove the first goal, which is X is in C?
Can I do cases prime?
Cases prime H at H, you mean?
Uh,
I mean,
yeah.
let's see. Cases prime at H. Yeah, it gives you a left and right, if you like. I mean, with like H, perhaps you wanted to do with H1 and H2 or something.
Yeah.
And now you can just copy H1, right? Or simply, you can also use this dot left notation, .1, or .1. So you can just write exact H.1. That would also does it for you. Because you just want to say, X in C, and H already has that. And here, exact H.2 would close the goal. Oh, it doesn't. So what's the goal here? X is in B. Now we have to prove X is in B. Oh, okay. Interesting. You see, because here the goal, so after constructor, the second goal, X is in B, right? Why is that? Because here we wanted to prove X is in C and X is in B. So H.2 doesn't do it because H.2 proves that X is in A only.
Wait, so H used to be the statement that A was a subset of B, and then we made H a different statement.
Great point. I think it was a bad practice from me. So I should have named this something else, right? Because that overlaps with our original H. And now once we did this, you can see that our original H got the name H dagger.
I see. Okay.
So
you could refer to that by calling it H dagger now.
Or H prime. So dagger is just, we cannot use dagger because that's reserved for Lean's internal representation.
I see. So that's just telling you that you have to fix it.
Yeah, exactly. But a better thing would be just give a different name, H prime, to not overlap. Mm-hmm. So now H prime 2 doesn't work. What can I do?
You could use like H prime 2 and H together somehow.
I think together would be something like this. It works.
Mm-hmm.
You're right.
Oh.
So cool. Yeah, why does it work though? Because H is an implication, right? It says if it's in A, it's in B. And whenever you have implication, you have this rule of implication elimination or modus ponens, which says, if I'm in A, then I'm in B, that I know. And if I apply that to the fact that I'm in A, then I will land in B, essentially. So this is H applied to that guy. If you like, you can also write apply H. And then your next goal is to prove you are in A, which you can get from H prime. So that's using apply. Okay, I don't think I have any time left. And what we essentially did, so let me recap what we did. We were in this file, Schroeder-Bernstein. We wanted to understand this ICC. The type of ICC was set N or set R or whatever, right? We didn't know what this thing means. And hopefully now we have some idea what set means. So in this case, it means it's just a subset of real line, right? Which satisfy the property that they are between 0 and 1. So that means if I give you some number between 0 and 1, and let's say that this 0 is a real number. So this would be, the real interval 0 and 1. What can we do with it? Actually, let's prove something, right? Now that we have the tools, we can at least do something. We can say at least, like, if I have ICO of 0 and 1, it's going to be a subset of ICC of 0 and 1. So let's see if we can prove this basic fact. How do I proceed here? So this is going to be the last thing we do, and then after that, lecture is over.
I guess we start by taking any element from the first interval. So intro some x.
Right. Intro x, great. Start. So just a real number. And now the goal is, if it belongs to the first interval, it belongs to the second interval. So let me just also introduce a hypothesis for implication at the same time. So we have x and hx, and x is, x is at least 1, but definitely less than 1. At least 0, but definitely less than 1. How do I prove that it's... So one thing you can do is just simplify ICC if you like. I mean, this is optional, doesn't have to. You don't have to, but it's helpful. And maybe you want to do dsimp ICO at hx. Okay, we just broke down what those intervals meant. And how do I prove that? So I'm proving an and usually we do constructor, and we have two subgoals now. The first is x is at least 0, and that I can get from hx. So you can just do exact hx.1. And now I have a goal that says x is at most 1. hx2 says x is less than 1. So I need some lemma that tells me if something is less than 1, then it's less than or equal to 1. How do I do that? So let me make a comment here. X less than or equal to 1 literally means that x is less than 1 or x is 1. Right? So therefore, we are trying to prove an OR statement. And we already know that x is less than 1. So I guess what we need is apply OR.inRight. Right? Oh, that didn't work. Or in left, maybe. Okay, that's not a good sign. It should work. Okay, maybe Lean doesn't exactly know that these two things are as definition equal. I see. I see the problem. Okay, anyway. Okay. So we need to say less than or equal of less than, something like that. Do we have a lemma like that? There is a lemma called less than or equal of less than, and that proves exactly what I want, right? But this is not rewrite. This is just implication. So I have to write apply this guy. Okay, now my goal, my goal changed. Before it was this goal, and I applied the lemma. Now I have a simpler goal, and that you can prove from exact hx2. Okay. Right. So now we are done with the proof, at least. Any questions before we go?